Ever wondered what the universe is made of? What if we told you that everything around you, from the air you breathe to the stars you see at night, is made up of tiny particles? Welcome to a journey into the minuscule, a voyage into the heart of matter itself. This is a world that exists far beyond the reach of the human eye, a world that holds the secrets to everything we see and experience. This, dear listeners, is the world of particles. The story of particles begins with a man named Democritus, an ancient Greek philosopher who, more than 2,000 years ago, proposed the concept of atoms. He believed that everything in the universe was made up of these tiny, indivisible particles. While he didn't have the technology to prove his theory, Democritus's ideas laid the groundwork for our modern understanding of the universe. Fast forward to the 19th century, and we find English scientist John Dalton. Dalton took Democritus's concept of atoms and made it scientific. He proposed that atoms were the smallest particles of matter, that they were indivisible, and that they combined in specific ratios to form compounds. For a while, atoms were considered the basic building blocks of everything. They were the smallest particles that could exist, the fundamental units of matter. The universe was like a giant Lego set, and atoms were the building blocks. But as our technology advanced and our understanding of the universe deepened, we began to see that there was more to the story. In the early 20th century, scientists discovered that atoms were not indivisible. In fact, they were made up of even smaller particles: electrons, protons, and neutrons. Suddenly, the universe seemed even more complex, more intricate than we could have imagined. It was as if we had opened a door to a whole new world, a tiny universe within the universe itself. So, atoms were considered the smallest particles, the building blocks of the universe. But as we delved deeper, we realized that there was much more to uncover. As our understanding grew, we discovered that atoms were not the end of the story. There were smaller particles, subatomic particles, hidden within. Imagine you're holding an apple. Now picture reducing this apple to its smallest constituents, atoms. Yet, if we delve deeper, we find that these atoms themselves are made up of even tinier particles. These are the subatomic particles: protons, neutrons, and electrons. Protons and neutrons reside in the atom's nucleus, a sort of command center, while electrons whiz around the nucleus, much like planets orbiting the sun. But what differentiates these particles from each other? The answer lies in their charge. Protons bear a positive charge, electrons a negative one, and neutrons carry no charge at all. This difference in charge is what gives rise to the electric forces that hold the atom together, much like an invisible glue. Yet, the subatomic world doesn't stop there. These protons and neutrons are further divisible into even tinier constituents, known as quarks. Quarks come in 6 flavors: up, down, charm, strange, top, and bottom. And they combine in specific ways to form protons and neutrons. In addition to this, there are other particles, like leptons, which include electrons and neutrinos, and are not made up of quarks. Leptons are unique because they do not experience the strong nuclear force, one of the fundamental forces of nature that holds atomic nuclei together. Then we have particles like mesons and baryons, which are made up of different combinations of quarks. Mesons, for instance, are made of a quark and an antiquark, while baryons, like protons and neutrons, are composed of 3 quarks. With the discovery of these particles, our understanding of the universe expanded, but we were just scratching the surface. The realm of subatomic particles is a window into the fundamental building blocks of the universe, a microcosm that holds the secrets to the macrocosm. We've come a long way in our understanding. Yet, there is still much to uncover in this intriguing realm of the infinitesimally small. Enter the world of quarks, particles even tinier than protons and neutrons. These minuscule particles are the building blocks of protons and neutrons, and were first theorized by Murray Gell-Mann and George Zweig in the 1960s. Their existence was confirmed later through high-energy particle experiments, and they have since been a fundamental piece of the standard model of particle physics. Quarks are unique in their properties. They carry a fractional electric charge, something unheard of before their discovery. They also possess a property called color charge, which has nothing to do with the colors we see, but is a whimsical term used to describe the strong force that binds quarks together within a particle. There are 6 types, or flavors, of quarks: up, down, charm, strange, top, and bottom. The up and down quarks are the lightest and most commonly found in the universe, making up the protons and neutrons in the atoms that form everything around us. Now, let's talk about strangeness. This is a property of certain quarks, specifically the strange quark. It's not strange in the way we usually use the word, but rather, it's a term used to describe a quark's ability to oscillate or change type. This property was named strangeness because it was found in particles that behaved in unexpected and strange ways in particle accelerators. Strange quarks, along with charm, top, and bottom quarks, are heavier and less common than up and down quarks. They are usually produced in high-energy reactions, like those in particle accelerators, and decay quickly into up and down quarks. Quarks opened up a new frontier in particle physics, but they were just one piece of a much larger puzzle. Their discovery led to a deeper understanding of the universe and paved the way for the discovery of even more particles, expanding our knowledge of the fundamental building blocks of matter. Imagine a particle and its antiparticle meeting and disappearing in a flash of energy. Sounds like science fiction, right? But it's not. It's called pair production and annihilation. So, what exactly is pair production? In simple terms, it's a phenomenon where energy is converted into matter. When a high-energy photon, a particle of light, encounters a nucleus, it can transform into a particle and its antiparticle. The photon essentially disappears, and in its place, we find an electron and its antiparticle, a positron. This transformation is a sublime example of Einstein's famous equation E-mc22, where energy, AE, can be converted into matter, M, and vice versa. But what happens when these newly formed particle pairs meet? They vanish in a process called annihilation. When an electron and a positron collide, they annihilate each other, disappearing and converting back into energy in the form of 2 photons. This beautiful dance between matter and energy is happening all around us, even though we can't see it with the naked eye. Now, you might be wondering, where does this happen in the real world? One of the most common applications of this phenomenon is in positron emission tomography, or PET scans, used in medical imaging. A radioactive tracer is introduced into the body, which emits positrons. These positrons meet electrons in the body and annihilate, emitting photons that are detected and used to create detailed images of the body's internal structures. This fascinating interplay between matter and energy isn't just a theoretical curiosity. It's a vital part of our understanding of the universe and provides practical applications in medicine and potentially in other fields in the future. Pair production and annihilation show us how energy and matter are interrelated, a concept that Einstein made famous with his equation, E=mc2. As we continue to explore the universe within, we come across particles that are yet to be discovered, the theoretical particles. These are not your everyday particles like protons, neutrons, or electrons. These are particles that have only been hypothesized, particles that we believe exist due to the clues they leave behind, or the gaps they fill in our understanding of the universe. One such particle is the graviton, a hypothetical particle that is thought to carry the force of gravity. If discovered, it would revolutionize our understanding of this fundamental force that binds the universe together. Then there's the tachyon, a particle that's always on the go, so much so that it's predicted to travel faster than light. While these particles may challenge our current understanding of physics, they could also open up new possibilities, like tachyonic communication, which would allow us to send messages faster than the speed of light. But it's not just about faster communication or understanding gravity. Theoretical particles could also help us answer some of the biggest questions in science. Take, for example, the axion, a particle proposed to solve the strong CP problem in quantum chromodynamics, or the sterile neutrino, which could be a candidate for dark matter, that elusive substance that makes up about a quarter of our universe, but has yet to be directly detected. The discovery of these theoretical particles could lead to a paradigm shift in physics, much like the discovery of the Higgs boson did. It could help us understand the very fabric of the universe, from the tiniest subatomic particles to the grandest cosmic structures. It could help us answer questions about the nature of dark matter, the origin of the universe, and more. The universe is full of mysteries, and as we continue to explore these tiny particles, we get closer to understanding the grand design of it all.